If you're a person and you're just chilling and you jump, gravity is still pulling on you. Gravity can act over a large distance. So just like that, the force due to an electric charge, so like this charge right here, can act over a large distance as well. So you might have noticed the little circle I drew around the charge. That is the field. That is what we define as a sphere of influence. So if an object is really close to it, it's very much affected. But if an object is far from it, then it is affected, but a lot less. So a good example would be if this guy right here just straight up, because he hates the entire classroom, decided to just let one loose. The guy right here is gonna think that he's getting like, this is like a murder attempt because of how strong it is, but the guy right here isn't really gonna notice. He's just gonna be chilling because this guy is very far from this, but this guy is like incredibly far, incredibly close. I mean, now how can we know and measure the electric field around a charge? We use something called a test charge. It's a small positive charge with no mass. It is too small to have a field of its own, and we give it the symbol Q. A test charge is always positive. It could be negative, but we just decided to make it positive. And because a test charge is always positive, if it's moving towards a charge, then we know that this charge has to be negative because it's attracting the positive charge. However, if it's being repelled by a charge or moving away from a charge, we know that this charge must be positive because it is actually repelling the positive charge. We refer to the object that the test charge is being involved with, or attracted, repelled, as the source charge because it's the source of what's attracting or repelling it. So steel ball has an unknown charge in it. Let's draw the steel ball, and we notice that the test charge, which is positive, is being repelled. Well, if it's being repelled, this has to be positive as well. And to measure an electric field, we use E with a vector over it is equal to Fe over Q. Now the arrow above the E shows this is a vector field, and you have to use it because if you don't use the arrow, the E here is energy. But if you do use the arrow, it's electric field. So let's just draw this out. This is 3.7 coulombs. This is, let's hope it fits, coulombs. It's to the right by 2.7 meters. And it's being attracted to it, which is 3.62 E10 newtons. Okay, so we already know what Fe is. Just plug that in. Divided by the charge. And for Q, we use what's being affected by it, what's inside the field, not what's producing the field. So we use 3.7. So to make it easier to understand, let's look at like F equals mg. If you're calculating the force, are you going to use the mass of Earth or the mass of the object being affected multiplied by g, which is 9.81? You're going to use the mass of the object, not Earth. And anyways, yeah, this gives you 9.78 times 10 to the power of 9 newtons per coulomb for the electric field. Oh yeah, the units for electric field are newtons per coulomb because, well, this is the force, so this is in newtons, and this is the charge, this is in coulombs, so newtons per coulomb. Now, if a source charge is positive, it's repelling the test charge, which is always positive. So this is how field around a positive charge will look. However, if it's negative, we know that it's going to be attracted. So we point the arrows towards it. So let's draw this out. The electric field is being created by a 7.5 coulomb charge, and it's pushing the test charge west, which in charge of that test charge is like 9.2 e negative 4, and the force is 2.1 newtons. So if we're trying to find the electric field, we can just plug in our values, so Fe over Q, and then it'll just be E. Electric field is Fe, so we're given that 2.1 over the charge, which is 9.2, E negative 4. That gives us 2.3 times 10 to the power of 3 newtons per coulomb. And the question already states it's being pushed west, but we know that regardless, because, well, it's going to be repelled by this charge. But anyways, yeah, west. Well, we know what the electric field is because we calculated that in the past question, and we know what Q is because it's stated. So E is equal to Fe over Q. Rearrange. E Q is equal to Fe. Use the same value for the electric field, and we get that it's 8.5 times 10 to the power of 3 newtons. Because it's in the same position, we know it's being pushed west. Alright, same thing. Fe is equal to EQ. Fe is equal to 2.3 times 10 to the 3 multiplied by the charge, which is now, and we always take the absolute value of Fe, so 4.81 times 10 to the power negative 2, and that gives us 1.1 times 10 to the 2 newtons east, because now it's being attracted to the charge, because we know it's negatively charged. So in this formula, we're going to assume that Q1 is the source charge, SC, and that Q2 is our test charge, so we're actually just going to remove the subscript of 2. So this will make E equal to KQ1 Q over R squared, and all of that over Q, then these cancel out. So then the electric field is equal to KQ1 over R squared. So the Q1 is our source, and then we just take the absolute value, because whether it's negative or positive does not matter. We just look at the electric field and then go from there for the direction of the field. So a tiny metal ball has a charge of 3.0 times 10 to the negative 6. We know what K is, we know that. And the radius, it says 30 centimeters, but we gotta use meters, so that'll be meters. And then the electric field is equal to KQ1 over R squared. So 8.99 times 10 to the power of 9 multiplied by Q1. And we always take the absolute value of it, so it doesn't really matter if we put the negative, because our answer has to be positive regardless. 0.3 squared, and then we get 3.0 times 10 to the power of 5 newtons per coulomb. And the tiny metal ball has a charge of a negative charge, so that means the arrows are going to be pointing towards it. So we just write inwards. So for these type of questions where there's multiple source charges, it's the same thing, you just do some vector addition. So the point is in the middle, right here, and the middle of the distance we just divide it by 2, and it is 0.29 meters. So let's just do the calculation for the blue thing first. So we just get KQ1 over R squared, is equal to 8.99 times 10 to the 9, Q1 being 1.2, all of that over 0.29 squared, which is 1.3 times 10 to the 11. And then the same thing here. Oh yeah, you can't forget the vectors. Is equal to K multiplied by 3.9. I don't know why that just happened. And oops, I did not mean to involve that. 4.2 times 10 to the 11. Okay, so now let's just, we know the one going here is 4.2 times 10 to the 11. The one attracted here is 1.3 times 10 to the 11. So let's just define the left direction as negative. So 4.2 times 10 to the 11 plus minus 1.3 times 10 to the 11, which gives us 2.9 times 10 to the 11 newtons per coulomb to the right, since this charge is stronger.